Imagine trying to teach a robot to navigate a new planet. You can't give it a map because you don't have one. Instead, the robot has to learn by simply trying things out. This is the core of reinforcement learning. In the world of AI, we often start with a model-based approach, where we know the rules of the game. But in the real world, we are often model-free. We don't have a perfect formula for how a patient will react to a treatment or how a customer will respond to an ad. We only have raw experience. To make sense of this experience, we use two legendary strategies. The first is Monte Carlo evaluation. Think of this like a student who waits until the very end of a final exam to see their grade. They run through an entire episode start to finish and then average the total rewards. It's simple and unbiased, but it's slow. You have to wait for the episode to end before you learn anything. The second strategy is temporal difference learning, or TD. This is the aha moment of reinforcement learning. Instead of waiting for the end of the exam, the TD learner updates their knowledge after every single question. It uses bootstrapping, taking a guess based on another guess. It looks at the reward it just got and combines it with its current estimate of what the future holds. But here's where it gets interesting. Even with the same data, these two methods can reach totally different conclusions. In a famous batch example, if a robot sees a path it has never taken before, Monte Carlo might assume the value is 0 because it has no finished history to look at. But TD learning is smarter. It uses the Markov Property to realize that if path A leads to path B, then path A is valuable because it knows path B is valuable. It connects the dots that Monte Carlo misses. Whether you choose the high-variance patience of Monte Carlo or the fast, efficiency-driven guesses of TD learning depends on one thing: how much you trust the underlying structure of your world.